Hello, everyone. Today, I'm happy to share some recent works about the topic alternative to inflation scenarios from DHOST Cosmology, which is based on the 3 papers. And here the talk is listed as following. Firstly, I will briefly introduce the alternative to inflation scenarios, meaning about its motivation as well as challenges. And then we introduce how we evade the instabilities plugged by on the alternative to inflation scenarios with the help of the DHOST cosmology, which is the main work of our research. And then I will briefly introduce the phenomenological study of our DHOST cosmology, and we summarize at the final stage. Firstly, we briefly introduce the motivation for the alternative to inflation scenario. Inflationary cosmology is currently the leading paradigm of the early universe cosmology, which predicts a period of time before the hot Big Bang, during which the universe undergoes near exponential expansions. And conceptually, it solves the flatness, horizon, and monopole problems, and as well as providing a mechanism for the formation of large-scale structures through primordial fluctuations. From observational sites, it predicts a near-scale invariant power spectrum of density perturbations, as well as a very small amount of primordial non-Gaussianities, which is in high agreement with current astrophysical observations. The motivation why we search for alternative to inflation paradigm is that, firstly, inflationary cosmology might introduce initial singularity at the far past. Also, to solve the flat and the horizon problem, we need large enough Ford number, which means that at the very early stage of inflation, the energy scale might exceed the Planck scale, which is the trans-Planckian problem. So firstly, we want to provide a possible solution to the initial singularity problem and the trans-Planckian problem. Secondly, alternative scenarios may provide distinctively phenomenological compared to inflation. And then finally, we may look out for the paradigm of inflation to judge where these solutions are economical or artificial, and then to measure the success of inflation. And we may classify the models for early universe scenario through the evolution of the scale factor A. In the following, I will briefly introduce 2 such scenarios. First is the bounce cosmology, in which the universe starts with a contraction period and then followed by an expansion period. And the second scenario is the so-called slow expansion contraction scenario, in which the universe starts in a quasi-Minkowskian configuration where the hyperparameter is approaching 0 at far past, but not exactly 0, then transits to an expansion period. This scenario is also named as an emergent universe scenario or Galilean genesis. And here I will give one exemplified bounce cosmology, and here the dynamics of the hyperparameter H is taken from our paper. I can see that the hyperparameter begins at the negative region at the far past and transits from negative to positive in a very quick manner, and then the universe keeps expansion. And this is exemplified Galilean genesis model, and the background dynamics is also taken from our paper. We can see that the scale factor at the far past is almost a constant, and also the hyperparameters is approaching 0. And at a quick transition near the time t equals 0, the universe then acquires a finite value of hyperparameter and it keeps expanding. And then we come to the challenges for the alternative scenarios. One main challenge is the so-called non-energy condition violation. We see that the equation of state parameters for the dominating matter content of the universe is inversely proportional to the square of the hyperparameter. So when the universe transits from a non-expanding state to an expanding state, the hyperparameter is approaching 0 and the equation of state parameter will approach to minus infinity, and then the non-energy condition is violated. This is a generic challenge for alternative inflation scenarios, which happens in which will happen in all the above two scenarios. And then when we come to constructing the alternative scenarios in so scalar tensor theory, that is, we add a scalar sector to the conventional gravity part provided of the general relativity and see whether the additional scalar can help to construct such scenarios. Firstly, NEC violation, you commonly accompanied with ghost degree of freedom, and it was found that the ghost condensation theory, where the scalar field have the non-canonical kinetic term and a trivial potential, is able to violate NEC without introducing the extra ghost degree of freedom. However, there will always exist gradient instabilities in which the sound speed of the scalar perturbations becomes negative within the framework of ghost condensation. So people believe that within the framework of Hondesky or Galilean theory, which is the extension of ghost condensation theory, the NEC can be stably violated and then resulting in a healthy alternative model. So this is the full Hondesky theory. Hondesky theory, by definition, is the most general scalar tensor theory, which with equation of motion up to second order, so that there will be no ghost degree of freedom. The Hondesky action is composed by 4 parts, and the specific form of the action is required to eliminate the higher order term in the equation of motion. And however, it was later found that the non-energy condition cannot be stably violated in Hondesky theory. More detailedly, there will be either ghost degree of freedom or a gradient instability within Hondesky theory. This theorem is proved to be true for DHOST cosmology, Genesis cosmology, as well as the Lorentzian wormhole. And then we come to our work. It is natural to guess if extending the Hondesky theorem could evade the no-go theorem. So, but however, modifying Hondesky theorem will lead to a higher order equation of motion. And generically, this means that there will be a gravity instability where there is exceptional ghost degree of freedoms. So to eliminate the ghost degree of freedom, the action should be in a certain specific form. And this kind of theory is dubbed as the degenerate Harvard-Steig tensor theory. And in our work, we show that some specific tensor theories can break the no-go theorem, and hence solve the gradient instability problem with no ghost degree of freedom introduced. So this is the most general action for scalar tensor theory, with derivatives up to second order, and the scalar field is at most quadratic powers. And to evade the stressing ghost, the form of the coupling AI is severely constrained. And in our model, we take a specific kind of DHOST action, which is in this form, and then we merge it with a certain type of Hondesky action, which is developed in previous studies and proved to be able to build up bonds and genesis cosmology. And since this is belongs to a DHOST theory, so merging it with the previous Hondesky action will not introduce ghost degree of freedom. And besides, when the coupling function f, which is generally related to the scale field as well as its kinetic terms, when the f is only dependent on the kinetic terms, the action does not change the background dynamics. So we mentioned that if the coupling f equals fx, then the DHOST action will correspond to the EFT operators, which contributes only to the sound speed of the scalar perturbation. And certain such operators are found to be able to remove the gradient instabilities in bounds cosmology. So we believe that the action LD can help to build a healthy alternative to inflation models. So this is the main results of our previous work. So here we show how the DHOST action can solve the gradient instability in bounds cosmology. The first figure is the situation where the DHOST action is absent, and we see that the sound speed squared of the scalar perturbation becomes negative at some certain ranges. But we provide three different DHOST couplings, and we show from the figure that the sound speed of scalar perturbation is always positive, and hence the gradient instability is removed. And also, we also show that the gradient instability problem in the emergent universe scenario can be also removed with the help of DHOST theory, and we deficit the evolution of the sound speed squared of both the scalar and the tensor sector here, and we see that both of them are always positive. And then finally, we briefly introduce the phenomenology of DHOST cosmology. One is the main results is that the DHOST action, if the coupling function f is only dependent on the kinetic term, has a negligible impact on observational signals. The reason is that for this kind of action, it will have a non-trivial contribution only during the transition period, which is generally very quick. So this effect is restricted by the short duration of the transition period. So we come to the conclusion that the DHOST action can serve as a mechanism to change the propagation speed of perimeter perturbation, evading the gradient instability without altering the other physics. And here finally, we briefly introduce some ongoing projects. So we see that the phenomenology of DHOST cosmology when f equals fx is limited. So we are searching for if there is new phenomenon with a generic DHOST coupling f when phi f is dependent on both the scalar field and its kinetics. We have already found that when f takes some certain forms, there will be more than one bounce phase. So it is interesting to study how to build up the multiple bounce cosmology with certain fx. Besides, we are interested to study whether certain f5 can help to acquire a scale invariant density spectrum, which cannot be achieved in conventional bounce and genesis models. So let's summarize the talk. Firstly, alternative inflation scenarios commonly requires an initial evaluation, which generally leads to ghost and gradient instabilities. And we introduce a type of DHOST action and construct stable cosmology models in bounds and genesis scenarios. And the DHOST coupling F equals Fx provides negligible phenomena, and we expect new phenomenologies for more generic such coupling. So that's all, and thank you for your attention.